afternoon. So today we are going to continue where we left off, okay, in our exploration of stochastic integrals. And in this class, we'll actually define the Ito integral, the Stratonovich integral, and see some examples. But first, I want to recap what we did last time. So we are thinking about SDEs, right, which we are going to write in this way, which we understand now is a notation, right, for really a stochastic integral. Right? And this dw is the Wiener increment, right, the random walk step. And now we know now that this is just a shorthand for the evolution of x, which will really be governed by integral of the right hand side, and the task is to understand the stochastic integral. So we started thinking about this. Okay, we have not yet defined it, but we just wanted to think it through and see what possible issues could arise. So in that process, we said, okay, I could think of writing this integral or defining it in terms of the limit of the Riemann sum. Okay, so if I look at that sum, sorry, I used, I think, small letters everywhere. Okay, so then I would have to evaluate B somewhere, right, and then multiply that with the Wiener increment delta W I. So when I divide the integral of time, right, maybe from t0 to t, for example, right, I would break it up into intervals. So I'll have the Wi minus 1, that is delta Wi, into B evaluated somewhere in that interval. So we said if we are going to choose alpha to be a fraction of the distance in that interval, then I could write it as Bi minus 1, right, that is B at t at I minus 1. So sorry, I used S here. So S is the integration variable inside, and this is also Fs. Okay, so I'll evaluate B at Si minus 1, right, that was the idea. And then I'll have plus alpha delta S, right, the step that corresponds to delta W, right, times dou B by dou S, right, again at Si minus 1. And then B also has a dependency on x, right. So I would get dou B by dou x, where I use a small x because B is a function of small x, but evaluated along the trajectory capital X, right. Again at this is at I minus 1. And now the important thing is this dx, right, I can replace with the SD. Okay, so this is 1, right, so this I can replace with equation 1, and then what we will see is that I will get a dw from there. Okay, so ultimately if I do this and then I look at the mean of the mean value of the integral, right, what I will get is these other terms will not survive, right, because delta S, delta W mean will become 0. Right? Any delta W by itself mean is 0. So the term that will survive from the correction will have this alpha, I'll get an alpha delta W square term B dou B by dou x. Right? This kind of term will survive in the mean, right, because this mean is not 0. Right? In fact, the mean of delta W square we know is delta T. Okay. So this sort of correction term will remain, which tells me that where I choose to evaluate the integral is going to matter. Right? I have not yet defined anything, but this already shows me that there will be this issue. Now, this I showed in the last class. What I want to do is to show you that it's not only when B depends on x that you get this problem, right? B, so here I have written it in a way that it comes naturally from the SD, but I could also just think of a stochastic integral separately, the way we think of, you know, a general integral. So suppose I had an integral that looked like this. Okay. So for example, right, you can say integral of sine x dx just as an integral. So here I thought of this integral as being coming directly from the SD, so that when I took this derivative, I replaced the dx. That's how I got this correction term. The dependence of B explicitly on time, which is deterministic, doesn't do anything. But here I want to just make the point that even if you by itself think of a stochastic integral without relating it necessarily to the SD, the same issue is going to arise, right? So I can think of, let's say, integral w dw, which we will do later, integral sine w dw, right? You're just treating w as a variable, except it's not a normal integral because this dw is the Wiener increment. Okay, it is w is the stochastic Wiener process, right? So the integral has to be treated specially. So even here you will have the same problem, right? So you have, why? Because I can again think of the sum. Again, I'll have delta wi, and now this b again can be evaluated anywhere, correct? And so if I write it as before, right, b at, so again I can put, this is a function of s, right? Again, same intervals. So you have time proceeding. As time proceeds, the Wiener process is also going forward, right, through increments delta w, and you're integrating with respect to that Wiener process some function of w. So now this thing will have the following, right, dou b by dou w, right, delta w times alpha, right, where alpha is again that fractional step that I'm taking. So once again, now when I take the mean, you will see that this term will survive, right, when I take the mean. So if I look at the mean, I will have a surviving term, which is like alpha delta w square, right? This will survive, dou b by dou w. Okay, so the point is that you cannot escape this issue of where the integrand function is being evaluated, provided that integrand function has some dependence on the stochastic process. Whether that dependence is coming directly on the Wiener process, because I want to evaluate such a function, I just specify b is some function of w like sine w, w square, whatever, directly dependent on the Wiener process, or indirectly through a stochastic process x, which itself is governed by an ST which depends on w. You see, so it doesn't matter how that dependence is coming in. If what the function you're integrating depends on the Wiener process directly or indirectly, you will have this problem about where that integrand function is being evaluated. Okay, if it's evaluated at the beginning, then the mean will become 0 of that integrand, right, because it's uncorrelated. But if you evaluate it anywhere other than at the beginning, right, by some fraction alpha, if you step into the interval, then you will have an issue because the value of that integrand will be correlated to the Wiener increment you tossed at the beginning of the interval. So the mean will not be 0. And you can correct for that by doing this operation, right, and then you find that there is a correction. Okay, so the mean is not 0. This is what I'm saying, right? The mean of this integral would be 0 if alpha is 0. That's what you're understanding. That makes sense, right? Because if alpha is 0, that means b is evaluated at the beginning of the interval, right? So only this term is there, and this term is uncorrelated to the random number I tossed at I minus 1, right, at that time. So if you take the mean, of course, it will go to 0. But if I don't evaluate bi at that point, right, I evaluate it somewhere in the future time within that interval, then the value of bi will depend on the Wiener increment I tossed at I minus 1. Right? So I took a random step that updated the Wiener process, and that update affected the value of b. So b is correlated to delta w at the beginning of the interval. Therefore, the mean will not be 0. Okay, how exactly that correction is, we sort of derived it, right, at leading order. In the limit of n going to infinity, you will get only this surviving. Higher order terms will drop out. That's the point. And that correlation can be either because b directly depends on w or indirectly through some SD. That's what we saw here. Okay, but either way, it's going to be there. All right, so now without having defined anything yet, we have just explored through the partial sum and recognized that we are going to have this issue. And therefore, if we want this SDE to make sense, we have to define what we mean by the stochastic integral. In other words, we have to make a choice, okay, of what this alpha should be. And at the end of the last class, I mentioned that there are two important choices, right, in stochastic calculus. One is the Ito definition, which takes alpha to be 0, right, and that is done because mathematically it's very convenient. When alpha is 0, all mean integrals become 0 immediately, right? And there are no correlations left, and that's easy to work with. As we will see in subsequent classes, all the stochastic calculus that we do, any calculations that we do, any manipulations of SDs that we do, are all possible only in the Ito case. All right. But what we will also see is that Ito integral, because of this behavior, right, it's kind of funny that all integrals will have zero average, that it cannot satisfy the usual rules of calculus when we do change of variables and so on. That requires the Stratonovich integral, and that corresponds to alpha equal to half for a reason that we will also see, okay, either in today's class or in the next class. So the message is we'll have to worry about two values of alpha, okay, that we will see as we go along. And all of what we're going to do in this class is to understand how to manipulate easily the Ito SD, and for physical applications, how to begin with the Stratonovich SD for reasons that we will see later, and how to convert it to Ito. Okay. And part of what I mean by manipulating the equations is ultimately to see how I can start with this SD and derive the corresponding Fokker-Planck equation. Okay, so that is the roadmap. But to go there, we need to develop some stochastic calculus. Right now, we have not even defined the integral. Okay, so let's do that. So now with this motivation, we will take the two definitions. First, the Ito integral. So now I'm going to actually define it. Okay, so the Ito integral is going to be defined by saying that I will always evaluate the integrand at the starting first point of the interval. Okay, so I'm going to say that it's the limit of n going to infinity, where n is the number of steps, but in the mean square sense. That's why I said mean square limit. So we'll see what that means in a second. So it's some appropriate way of taking the limit of the number of steps of the integral going to infinity, where the partial sum is being defined as I going from 1 to n, right, number of steps. And then I discretize this, right? So it's going to be G at S evaluated at I minus 1, like I said, right, at the beginning of the interval, times delta Wi, which is Wi minus Wi minus 1. Okay, or W at Si and W at Si minus 1, same thing. So instead of using limit 2 times, I'll just say okay, the mean square limit. Okay, and what does this thing mean? So now I'm giving you the definition of mean square limit, right? So if I have some object xn, right, which exists for any n, and as I take n tend to infinity, its mean square limit is x, provided the following is true, okay, that the error okay, the variance of the errors go to 0. Okay, so it's like mean square convergence. And this sort of definition is in fact similar to the mean square convergence in Hilbert space. So those have done some functional analysis. You know that in Hilbert space, where we define the suitable norm, right? In Hilbert space, it's the 2 norm, and that there we will define convergence in the mean square sense. So, for example, you can get a solution to the diffusion equation using separation of variables, right, as a Fourier series, right, if you do periodic boundary conditions. So that is a solution in the sense that if you take enough Fourier terms, you will converge to the exact solution, but only in the mean square sense, not in the pointwise. So this is the same sort of idea here, but here it's mean square statistically. Okay? So if you like, I will have different realizations of xn because it's a stochastic process. Right? So, and then as n goes to infinity, those stochastic realizations converge to some other stochastic quantity, in the sense that if I take the difference between these things, there will be some errors, but those errors have zero variance as n goes to infinity. Okay, because after all, we are comparing stochastic things. There is no one answer. So it's not converging to something definite. It is converging to some other stochastic process, right? And then my point is, though it's identical in the sense that the errors have zero variance. Yes.
In Riemann language, it is basically what it is when n reaches infinity. Is it so?
So I don't understand the question.
Basically, in Riemann language, this mh limit means that the value that it takes when n tends to infinity.
No. That is just a definition. No? That is this. Okay. The point is that, first of all, there is no value. It's a stochastic quantity. Okay, so you imagine something stochastic. There's no one value, right? So as n goes to infinity, it will be something, of course. That something has to approach the right-hand side such that the errors are zero in the variance. I cannot say it any clearer than that. You have to think about it a bit. But so in other words, if you look at this quantity, right, I construct this, you understand this, no? I'll construct this partial sum, okay? As n tends to infinity, this thing will converge to something, okay? That something will be this integral. Now there is no one answer, right? It's not like saying I'm doing integral of, let's say we had integral x dx is x square. When you did the Riemann integral, you will look for exactly x square. So you should converge to x square as n goes to infinity, no question. Now here there is no such thing, right? The answer of this integral, whatever is some stochastic object, right? Its answer will change every time I do a realization of the Wiener process. So let's say I take time t0 to t, say 0 to 1 is my time interval. Right? So as I go from 0 to 1, I will generate a Wiener trajectory. That means I take random steps, I get a random walk trajectory, that is w of t, right? And its steps that I used is dw. So with respect to that particular random walk realization, I will integrate this function. Maybe it is sine w, maybe it is governed by some differential equation, right? So each time I generate a random walk, I can calculate this integral relative to that random walk. I'll get one number. But I repeat the random walk, I'll get another number. So I'll get another number. So that will have some distribution, right? That is the meaning of this quantity. It is still stochastic. And what I'm saying is whatever that is, right, can be realized by breaking it up into the partial sum, taking the sum intervals arbitrarily small, so n goes to infinity. And then I'll get a bunch of numbers here. Those numbers minus, if I somehow knew the correct answer, those numbers, if I subtract it, I'll get some errors. The variance of those errors must go to 0. Okay. So the definition is only statistical, right? Because it is stochastic. It's not one number. So that is it. See, your mind will try to tell you to think of the integral the way you think of normal integrals, right? You have to overcome that idea, right? Every quantity that you see is something fluctuating. There's not one answer. And so when you say something is equal to something, it is only in a statistical sense. So in the calculus, we will use equal to henceforth. But what we really mean is that that it's equal only in this mean square statistical sense. Otherwise, it doesn't have any meaning. Okay. So this is the definition of the E2 integral, right? Yes, the other caveat I need to make is about g, right? So g should be a non-anticipatory function. Right? Without a formal definition, what it just means is that the value of g at some time t should not depend on the future, okay, which is usually the case in any physical problem. The reason is that only then this and this are uncorrelated. Okay, that's the idea. So if g at si minus 1 somehow depended on g at a future s, but then that value will be correlated to this, right? So these two would become correlated. But of course, in any physical problem, that doesn't happen. So as long as all the problems we'll be considering, this integrand will be some function of Si minus 1 and past time. Right? For example, here, correct, the b depends on x. Right? So when we come to b at Si minus 1, b depends on x at Si minus 1, but x at Si minus 1 depends on the past. So the value of b here at Si minus 1 is correlated to the previous time. But it should not be correlated to the future time. Only in that case, this delta W average is 0. Okay, so that's what we mean by non-anticipatory. So I will not say this again because this is what the case is going to be during the course. Okay, so with those conditions, this is the definition of the Ito integral. The main point to keep in mind is that g must be evaluated at the start of the interval at I minus 1, and therefore it will be uncorrelated to this increment. Right? And then the mean of this integral will always be 0 because of the way I have chosen to evaluate the g. So that is the first immediate property of the Ito integral. Okay, and the other point is that it is defined in this kind of mean square limit sense. So what I was doing here to motivate is to look at, so I use the same partial sum idea, correct? That's like what is written there. But what I did not do, since this is not a proof, right? What I did not do is I just took the mean value of this. And I showed you that the mean value will be 0, but it will have some correction. But when I want to calculate the Ito integral, I can't just look at its mean. No? It's just telling me the mean value. But that integrand, which is a stochastic quantity, will have a mean, yes, but it will also have a variance. It will have other moments. It will have a full distribution. So just looking at the mean, it's not enough. So the definition doesn't look at just the mean, right? The definition is looking at this mean square limit where the errors variance has to be shown to go to 0. So for example, if I tell you, which we will do next, right, that integral w dw is equal to w square by 2, which is what we know from usual calculus. If I had to check that, I would have to check that the errors are actually becoming 0 as n goes to infinity. So that's what we're going to do now. So anyway, when we'll do some problems so that this definition makes sense, and also it will drive home the idea of the weirdness of these integrals. Okay, so if you are still a little uncomfortable with the definition, let's not worry about it because we will now do a couple of examples which will clarify things. So let's do an example. Okay, so let's consider this integral w dw from t0 to t. What would be the answer of this for a usual integral, a usual Riemann non-stochastic integral, if w was just some variable? Right, so you would just have correct? This would be the normal answer. Okay, so now we will check whether it is this or something else and how to actually calculate it. Okay, so to do this, we have to, so the way this, of course, in practice, nobody calculates integrals like this. This is just to give us a feel for things, okay? So, but if we had to do something like this, you would have to show that this integral minus some guess of the answer, those errors are going to 0, right? The variance is going to 0. So I first need to guess the answer, right? I cannot derive it directly. In fact, how do we do integrals, right? That's, now we have forgotten because we did it maybe in school. But when you first did integrals, you have to actually do the Riemann sum, do some manipulation, but that's not how you normally do it. No, you do it by inverting derivatives. Right? So you know that derivative of x square is 2x, and then you realize, okay, that therefore the integral of x is x squared by 2. So, and then we remembered all these rules, and that's how we did integrals. But you don't actually do integrals using the definition because that's quite cumbersome. So, but now we're going to actually use the definition just to understand the definition. Okay, and then later on in practice, we will not actually be doing things this way. Okay, so we know that ultimately I have to deal with a partial sum. So let us examine the partial sum. Just like before, that gave us a clue about things. This it will do the same here. So the partial sum, that would correspond to discretization of that, right? So delta Wi is Wi minus Wi minus 1. This corresponds to this. And W should be evaluated where? At I minus 1, correct? Okay. Now to make progress, so again, as before, I would like to get some clue, I would like to look at the mean value of the partial sum. Even though that doesn't give me the answer directly, it will again give me some hint as to what maybe the answer could be. Okay. So if I try to take mean of this, I can't do anything much because this is a product. Okay. It will, of course, tell me the answer is 0, but doesn't give me much insight. So what I would like to do is expand this out. So we will complete the square. Remember this trick? Yeah. So we will write this as half, so it becomes 2ab, and then we can complete the square as this square plus this square, right? And then you subtract out. Sorry. Okay. But what is this? You will see that delta Wi plus Wi minus 1 is nothing but Wi, right? So you will get half, again, summation right from there. Okay. So now you recognize, if I look at these two guys, when I take the partial sum, I will have, so if I look at it from the bottom, from the top, right, I'll have W at t the whole square by 2 minus W at t I minus 1, but then W at t I minus 1, W, so they will start cancelling out. So in the end, this thing is just going to be equal to W at t, and this will be the first interval. And then here I'll have minus summation okay. So this is Sn. So I've not done anything now. I started with the partial sum, which is the discretization of that integral, okay? And I was able to manipulate it and get finally that there are two parts of the partial sum that are independent of n, right? W square minus W at t naught square by 2, okay? So now if I take the mean square limit of n going to infinity, this will not change. So this is definitely part of the answer. Only this thing is there, which has an n dependence, okay? And this will presumably modify the answer of the integral from the Riemann integral. Okay, so the first two parts is what I would have normally got if I did a normal integral. Right? In fact, to get this answer, if I didn't use inverse differentiation, right, I would do exactly this. If I treat it as a normal integral, I would use the exact same steps and realize I have reached here. But if instead of dw, if I had dt, correct? When I was doing, suppose I was doing integral t dt, right, in time, or if w was just a stand-in for a normal deterministic integration variable, okay, then what would happen is I would say, oh, see, this is delta w square, it's second order, right? So then I would, if it was a normal thing, I would write it as a total interval divided by n square, and as n goes to infinity, this thing will drop off. That's why when you do the normal Riemann integral, this thing is low order, it drops out, okay, and the answer would be this. But here, that is not the case, right? Because delta w, it does not go as dt. Delta w square is not like dt square. In fact, what do we know? We know that the mean, right, is what? This we know, correct? Right? And therefore, we know that the mean of this stuff, right, is going to be t minus t naught, right? Because it will become summation of the delta t's. So it will be the full time interval by 2. So in other words, I can already see that if I look at the mean of Sn, I would get these two terms, right? And I would get minus t naught by 2. That's what the mean would be, okay? Because delta w, remember, does not go like dt, it goes like root dt. That's why that term is not dropping out. In a normal integral, that small derivative would, if I had done, w was just like time, right? This would be like dt square by 2, and it would drop out. But now it is going like dt, okay, because it is the Wiener process increment, right, whose standard deviation is root delta t. So when we use this fact, we will anticipate that the mean of Sn would have this minus t naught by 2 sitting there. So therefore, let's take that as a guess. Right? What we have calculated is the mean of Sn. Right? So now I know that the mean of Sn okay, this I know. And the mean is independent of n. This does not mean that Sn is equal to this, right? So I still have to prove that, but I have able to derive this. So therefore, a good guess is to say Sn is in fact that. Okay, so I can now guess that the answer, right, that the answer of that integrand is this, and then I can try to prove it, okay, by looking for the errors. Okay, so we are going to guess that this integral and I now need to prove this. Okay, so to prove that this is the answer to this guy, what I should do is take the partial sum, subtract the partial sum from that, square ensemble average, and check the limit of n going to infinity. Okay, now I already know that the partial sum will exactly evaluate to this, right? And this stuff will cancel the first two. So what I really need to prove is just this latter part, right? Right, so this whole quantity has to be equal to t minus t naught by 2. In the sense that the difference between them, ensemble average, right, should go to 0 in the mean square limit. As n goes to infinity. Okay, then I would have proved the integral. So what I know is that the average of this becomes t minus t naught by 2. Okay, but is it actually equal to that in the mean square limit is the question. Okay, any questions? So now we have to do some algebra to figure that out. But what I wanted to keep in mind, other than don't get lost in the algebra, try to understand, right? Follow what the general drift is. Okay. So this part follows as we have always done, correct? That's why I'm not worried about it. It's only the behavior of this guy. Okay, and we now want to, we have already anticipated that the mean of it will be t minus t naught by 2. Okay, it also makes sense if you think about it heuristically that the Wiener increment delta w behaves like root dt. But now I want to actually prove it according to the Ito definition. For that, I need to show that the errors between this partial sum of the Wiener increment squared and t minus t naught by 2, that those errors go to 0 in the sense that the variance goes to 0 as n goes to infinity. This is the idea. Okay. So let's do that now. I'll go to the other board. Okay, so let's consider that quantity. And I had the mean. Okay, I removed the by 2. Okay, that anyway it doesn't matter.
Sir, was the summation inside the square or outside the square?
Sorry?
Was the summation inside the square or outside the square?
Sorry, correct, inside this. Okay, so it's summation, this is all one, summation of right of I going from 1 to n. Okay, that's how it is. Okay, in this whole thing, I have taken a square. And then I take the ensemble average. Okay, so let's bring the square in. Okay, so this is like a plus b the whole square, but this is of course got many, many terms. So I will square each of the terms first. So I going from 1 to n, I'll have delta wi to the 4th power, okay, plus now t minus t naught, the whole square. Okay, so it's this square, and then I have to do minus 2 times this into this, correct? And I have another term, right? Because this is the whole sequence of terms. So all of them have to be taken together. Okay, so this makes sure I'm not double counting, right? So I take delta W1 into 0 because there's nothing below it. Then I'll have delta W2 square to delta W1, and then 3, 2, 4, so on, okay? And this is the multiplications of each of those increments with delta T. And all of this is under the ensemble average. Okay, so now I have broken it up into individual terms. I can take the ensemble average on each, right, and see how it's simplified. That's the idea of these calculations. Now the only thing everything is delta W squared, which I know is going to be like delta T. Right? That I know exactly because it's a Wiener process, which is a Gaussian. Right? I need to know what to do with this delta W to the fourth power. Does anyone know what any special property of the fourth moment of the Gaussian? So one property of the Gaussian is that all its higher moments are defined by just specifying the mean and the variance. Right? So mean is 0, variance we know. Right? And so for a Gaussian, in general, right, and therefore because delta W is a Gaussian, the fourth moment is thrice the second moment. Okay. Okay, and of course I also know now that any second moment is delta T. Okay, this is what, these are the properties of the Wiener process. Ah, sorry, I forgot the square on top, otherwise the powers would not match. Okay, just pay attention to this, right? That so the fourth moment is 3 times the second moment squared. Okay, otherwise the powers wouldn't match. Fine. So now I can proceed, right? The first guy will give me summation of I going from 1 to n. This will 3 times, right, delta T I square. Okay. So that is one term. Sorry, I've already acted the ensemble average. Okay, so this is the first term. T minus T naught the whole square I have sitting here. Okay. Minus 2, what do I have here is T minus T naught. Okay. Now in this sum, each of the delta Wi squares will become delta Ti. So it's summation of delta Ti, which is T minus T naught. Okay. Into this. So I'll get 2 T minus T naught squared. Okay. Plus now 2 times this double summation okay. So see now already, so our goal is what now we want to show this is becoming 0 as n goes to infinity. Okay. So you can see that these two are going to cancel and leave me 1 minus T naught. Okay. Then I have these two terms left. So what should I do with this? Remember this came from expanding the square. Okay. So but I have delta T sitting there. So if I take 1 summation delta Ti square plus this, it will actually be summation delta Ti the whole square, right? Just the same logic I used to write this if I invert it back, right? So let me say it, right? So we'll use the fact that summation delta Ti the whole square is equal to right, that exact summation I j I minus 1 n. Correct? So I can move one of these guys along with this and I'll get summation delta T the whole square, but that is just T minus T naught the whole square. Correct? So after I use all of that, I'm going to get, so this minus 2 will cancel with this and with the T minus T naught square coming from here. So in the end, I'm just going to get summation 2 times delta Ti square. Okay, and now what is this? This thing will of course go to 0 as n goes to infinity, okay, because it is delta Ti square. Right? Now we don't have delta T anymore. Okay, because so of course in the limit of for equal intervals, right, delta Ti square is just T minus T naught divided by n, right? Right, and the summation of that will be n times that, but you still have a 1 over n, and that will go to 0. Okay, and even if you take unequal intervals, it doesn't matter. You can still bound the integral and show that it will decay to 0. Right? I mean, you can still bound the sum and show that it will go to 0. The main point is that when you see delta t squared, this obviously behaves like 1 by n squared. So when you do n sum it n times, it's still going to decay to 0. Right? What survives is things that go like delta t. And those terms are sitting here, right? So that we got rid of. Those cancelled out, the terms that would survive. So what remains is something that becomes smaller and smaller as n increases and will ultimately become 0. Okay? So what we have done now is we have proved indeed that the difference of summation delta wi squared and t minus t naught, that those errors go to 0 in the mean square limit sense. And so with this we have proved now that the Ito integral, okay, right, minus t naught by 2. This is the actual Ito integral, okay, which differs from the usual non-stochastic integral by that factor t minus t naught by 2. Okay, and I should not check the mean, right? Because I know by definition that the mean of any Ito integral is 0. Therefore, the mean of this should also be 0. Right? So can you see that it is 0? So if I take the mean, I know this is 0, right, by definition. Right, because I know the Wi is always evaluated at I minus 1, which is uncorrelated with delta Wi. So definitely it has to be 0. But now that I've got the answer, I should verify. Right? And this is, right, so this is the LHS. And the RHS, if I look at it, is the mean of W square, right, T. And what is this? I know the mean of what is the mean of the Wiener process squared? That is like the mean square displacement of the Brownian walk, which is exactly T. Right? It depends on how much time you have advanced the Wiener process. So this will exactly be T, this will exactly be T naught, and so they'll of course cancel and you will get 0, right, as you should. But that we already knew because we anticipated the answer by looking at the mean of the partial sum. Okay, so now you can see that this E2 integral is a strange object, right? We have done, so today in this class, some amount of tedious, boring algebra, but the outcome now we should take some time to appreciate, okay? So we can already see in this simple example that the stochastic integrals have answers which differ from usual integrals, okay? And the root cause of that, of course, is that the stochastic integral depends on how we choose to evaluate the integrand, right, in the partial sum. In other words, there is no unique stochastic integral. One has to define it by choice. And because when we choose the E2 integral, so maybe there is some choice which will give you the same answer as usual calculus. In fact, that's what we'll see next. But at least in the case of the E2 integral, we know that we have made the choice according to which the mean value of any stochastic E2 integral is 0. Right? Now, of course, the normal answer from calculus for any integral will not have 0, right, in general. So if I do some integral treating w as just a usual integrand variable, I will get some answer. Why should that be 0? Why should the mean of that be 0? Right? Of course, it will not be in general. So therefore, in general, for sure, the answer you get from from E2 integrals will not match the usual integral answer, right? Because E2 integrals have to have 0 mean. Okay. So in this particular example, we can see that the usual Riemann integral answer, the usual non-stochastic answer, is complemented by a t minus t naught by 2, which is exactly what is needed to put the mean to 0. Okay. So in fact, we could have anticipated that answer in some sense, right? Because when we saw this Riemann part, we know the average of this already would be this, and so we knew it should have to have that extra thing, otherwise it will not go to 0. Okay, but we also proved it properly. And all of this funny behavior is coming because you're integrating with respect to this stochastic Wiener increment, which is uncorrelated at every instant of time. So this is what I wanted to not lose sight of, right? So we are discussing many things, but the heart of all of this is because we have made this uncorrelated assumption, white noise assumption about the stochastic process, right? We are saying that at every time, the delta W that I'm tossing is uncorrelated to the past. It is this that is giving you 0 mean. Okay, this is crucial. And it's only that limit, taking that white noise limit, that allows us to get these funny but also helpful properties. Because I can actually, the fact, so what you should, there are two ways of looking at it, right? One is to say, okay, stochastic calculus is more messy and more complicated than usual integral calculus, because I have some other weird terms. I have to do all this mean square limit business to get an answer. The flip way of looking at it is it's quite miraculous that if you're looking at the integral with some stochastic process, which is literally a random, you're integrating with respect to some random numbers, that you can actually write down analytically an answer, which is in any sense exact. Right? So if you think about it like that, it is quite remarkable that you can write down an answer for something at all, right? And one that is relatively closely related to what you already understand. Okay, because if you think about what you're doing, I'm generating some Brownian trajectory, right, which is composed of small steps. And I tell you, okay, multiply each of these steps with some arbitrary function and define an integral, okay, which I can define by taking those steps as small as I like. Whereas the integral you're usually used to is saying, okay, I have the number line, multiply intervals of the number line, which you can say is time, right? So take the time as the number line, you multiply each element with something, and you can, of course, you'll get some answer. Right? That is the usual Riemann integral, and you prove things about it and so on. Now I'm taking that smooth number line and replacing it with some weird stochastic trajectory. Why should I get any kind of definite answer? Or even if I can, of course, compute something, but can I a priori tell you what that answer is going to be in any sense? Or will it always be numerical? So normally if you think of, okay, I want to solve some model and I will treat it stochastically, right? A priori one might think, okay, I have to just give up doing anything analytically, I just have to do numerical simulations. And from a numerical perspective, it's okay, fine. Instead of just evaluating a usual ODE, I'll just add some random number and see what happens. And I can do computations, etc. Right? So you can always compute an integral. That is not surprising. Right? What is surprising is that without computation, I can tell you the answer. Even if that answer happens to be in some statistical sense, right? But still it is amazing. And that we're able to do only because we have made the big simplification of the white in time. That means each increment is uncorrelated. That was the importance of taking that white noise thing right at the beginning when we started SDs. That is what allows me to do all this stuff, right? Because you see here, I can always do these operations till here. But what simplified things is when I took the ensemble average inside, I could say that, right, this is uncorrelated, these two guys are uncorrelated with each other. That's why I could take the ensemble average inside the product and apply it separately to each term. That's only if the linear increments are uncorrelated. Okay? Right, same for the sum, right? If I look at this sum, I can take the ensemble average inside because the subsequent linear increments are completely uncorrelated. So when I sum them, it's a sum of the variances or sum of the fourth moments. That's only because they're uncorrelated, right? Otherwise, I cannot do anything. So suppose I had said, okay, I now want to think of some Brownian walk modified version where each increment has some dependence on the past increments. A simple way to do this is you generate a usual Brownian trajectory, and now you modify it by saying each future increment is some combination of the previous ones. Or you can weight it, right? You take a next step as some weighted sum of a random number toss and my previous step. You will get a correlated time series. So you can have correlated random walks. If you do this, you cannot do anything anymore, right? It becomes fully numerical. Okay, so this is the crucial step, which right in the beginning Einstein did, right? When he did his derivation, it relied on the fact that he was taking these steps of size delta, which were uncorrelated, and then he was able to make progress. The same thing we kind of assumed in Langevins derivation and so on. And that's exactly what we need to be able to make any kind of progress with the stochastic SD. Okay, so it's a simple thing, but I just wanted to realize what we have done. So we have been able to write down in some fashion, like our usual calculus, some integral. Okay, we have given it some meaning, even though this thing, when you see this, you should think dw over time means infinite, I mean a huge number of Brownian trajectories, all of which are completely different. Okay, and I'm getting, if I integrate over it, I'll get different answers, all of which are kind of randomly fluctuating. And this has only some sense in the statistics of that distribution of this thing. Right? And with all that complexity, I can write down that this is going to be the answer. In the sense that if I now take each of those trajectories, which I use to construct the integral, I put them here, right? And I evaluate this, I subtract that, I'll get a bunch of numbers. And those numbers will match these numbers in the sense that the errors will have zero variance. Okay. So that I think is quite remarkable. Fine, but now we still have to understand, okay, so at least we have defined now what is E2 integral, and we have seen the evaluation of one E2 integral. Okay. Now the point of this course is not to become masters at evaluating E2 integrals of this style. Okay. Ultimately, we want to use E2 integral and E2 calculus to go back to SDs. Okay. But this exercise is just, hopefully now the difference of this E2 definition from the usual integral will sink in. Okay. And also, why typically it's going to be different from the usual answer. Any questions? Okay, so now as a reward for going through this difficult calculation, we'll do something even more interesting and remarkable, but much shorter. Okay, we will take a look at the Stratonovich integral, which is going to be now analogous to this, except instead of evaluating the integrand at I minus 1, we'll do it at the midpoint, because I remember alpha equal to 2 is what we had motivated, right? But without justification. So now we will see that the Stratonovich definition will show something unique in the specific case of this example, okay? But it's a general property. Let us see that. So we saw the E2 definition. Let us look at the Stratonovich definition. Okay, in the usual nomenclature, I mean, it depends, different people do different things, but Yeah, okay. So the way we'll designate Stratonovich is where we just write G of S, right, dW of S earlier. We'll now put a small circle, okay, between the product. So this will imply that when we see these two things under the integral, the G must be evaluated not at the starting point, but at the midpoint, okay. Okay, so this is going to be equal to now, again, mean square limit, right, same sense, the partial sum, and this time G will be the, so it's, I mean, I say midpoint loosely, but G is not actually evaluated at the midpoint as we have been motivating, but more precisely what it is that it's the mean sum and so under some cases it's the same as taking the midpoint, others it's not. Wait, sorry, that is not correct. Let me be a bit more careful. Okay. So of course, I should not say G is only a function of S, right? In the Ito case, it did matter, but here it's going to be important that it depends on some other stochastic process X, which could also be directly dependent on W, comma S. Because it's this stochastic dependence that gives me the effect of where I evaluate it. And then when I come here, it's going to be G. Now, so it's not G is not summed, but G is evaluated at the mean of X, okay? Okay, so the point I was trying to make is that G is not evaluated at S I plus 1 minus Si by 2, right? That would be like evaluating at the midpoint of S. That's not what's happening. G is evaluated at the mean location of X, okay, where X is its dependence on either X is like, for example, in an SDE, that's how we'll encounter it. But instead of X, I could have just had W, that G depends on W. Right? In that case, the G that I use in my partial sum is going to be the value of G at Wi minus 1 plus Wi divided by 2. Okay? And this S, second S, denotes the explicit time dependence. That anyway does not matter. But as we saw earlier, whether I could put Si minus 1, I could put Si also, it will not matter. Because the explicit dependence of time has an error that will go like delta t square when we look at the variance. That will drop out. And then this is the usual Wiener increment. Okay, and now the important point is because this G is evaluated, or the G that I'm using is somewhere after I minus 1. It will therefore be correlated with the Wiener increment. Okay, so this is delta Wi, right? The delta Wi is the Gaussian random number that I've tossed. So whatever I toss will affect X at the future time. And because G depends on that, this G value depends on this increment. So when I take the average, it will not be 0. So the average of Stratonovich integrals do not have to be 0, unlike the Ito case. Now the question is, why did I choose this 1 by 2, right? It's like taking alpha equal to half in some way. I can choose any other combination. Okay, so it turns out that this is the combination that gives you integral answers which are the same as your usual calculus. And not just that, all the usual calculus rules that you have in transforming differential equations will apply to Stratonovich integrals and Stratonovich SDs. We will prove that, or we will see it later on. Not prove, but we will at least see it more clearly. Okay. But for now, let us take the definition and let us apply it at least to that example and see whether we get the usual answer. Okay, so I'll let you, try this out. So the example is, remember, is integral W, but this time I have the Stratonovich version, so I put the circle. So this circle means I'm going to do it in the Stratonovich sense. Okay, so to find the answer, I should now consider, okay, Sn, the partial sum, just like I did before, right? And now you see what this W should be evaluated at, according to that definition, right, as the sum of the two extremes. Correct? And this is delta Wi, which I could write it as delta Wi, but if you see this, it will be convenient to write it in this way. Okay? And now if you're paying attention, you will immediately recognize that what's about to happen, right? This thing is going to become summation I going from 1 to n Wi squared by 2 minus Wi minus 1 square by 2. And then again, when I sum it, the intermediate guys will cancel, so I'll get W at t square by 2 minus W at t naught square by 2, which is the exact usual Riemann answer. Okay, so the whole difference lied in where I evaluated the W. The whole difference lies there, right? So in the case of the Ito case, this was just Wi minus 1. And I had this stuff, I couldn't do anything with it. Then I expanded this, I completed the square, etc. And that threw out this answer, but with the t minus t naught by 2. But now, because in the Ito case, I don't use W at I minus 1, instead I take the mean, right? The halfway mean. Then immediately it gives me the usual answer. Okay. Now, in this case, it looks like a trick. Okay, of course, it doesn't mean that in all integrals it will give the usual answer just from this. Okay, but it turns out that it does. And we will see why in the forthcoming classes. Okay. But at least in this specific case, you can see that now I have two different definitions of the integral, right? The Ito and the Stratonovich. Ito, I know a priori the average should be 0. Stratonovich, there is no such thing, no such requirement. Okay? And in the specific example of integral W dW, we see the Ito answer differs from the Stratonovich answer, the Stratonovich one being the same as my usual integral answer. Okay. So in this class, these points are just meant to drive home the idea that Stratonovich integrals depend on how you define them, right? And then the answer depends on that. And the Ito case is a simple one. It has always 0 mean, but that means that your answers will always be different. I mean, in general, they will be different from the usual calculus answers. Right? But now I am saying, which on faith that you have to take, but we will see later, that in the Stratonovich case, however, gives you the usual integral answers. And therefore, the mean is not 0 in general. Yes? Of the stochastic process in the interval, yeah.
Whereas there you're getting Wi plus Wi minus 1, which to me seems you're taking the.
No, it's the exact same thing. If G is, so if X is W, and if G is just identity, this is it. If the function G is, if X is W, and the function G is just W, then that's what I've done. Right? Now, if I was integrating sine W, right, I would then say sine of this. Okay. or later when it will be b of x comma s, right? Then b will be evaluated at x plus dx by 2. Okay, and then that dx we will use the SD. That's what we'll do later on. Okay, so it may seem surprising why this factor of 2 should give you the same answer in general as usual calculus. We will see, again, I will not be able to prove it in some rigorous way, but we will see various motivations. Okay. But one, you can already start to get some idea, okay, since we have 5 minutes. So if you look at what gave rise to this correction in the Ito case, right? This t minus t naught. So that came because remember that when I do this partial sum, I will ultimately retain all things up to order delta t. Right? Anything of higher order than delta t will vanish as n goes to infinity. That's what happened here. Right? So this stuff went off. So this extra thing is coming from delta w squared, right? Because remember the Wiener process, so as you will see, again, I'll formalize it in the next class, right? But the whole idea of stochastic calculus becomes very simple once you recognize that dw behaves like root dt. This is the kind of heuristic rule to make, to get intuition about these results, okay? So, and we've already seen that in fact, by itself, if you think of delta w, the increments of the Wiener process, their standard deviation in fact is delta t. The variance, sorry, root delta t. The variance of the Wiener process is delta t, right? We've in fact used that here, correct? This is an exact result. Okay. Therefore, the square root of this will go like root dt. Okay, the standard deviation of delta wi goes like root dt. Now, what we have, that's true here. What we cannot prove in general from this simple thing is if I multiply this by some function, that will still hold, right? That's why we had to prove this in each case and so on. But what I'm saying is intuitively, if you think of it this way, okay, you can still intuitively say that if I have something like g delta wi square is going to behave like g delta t, right? And that's why that delta t survives. When you have delta wi square, that will survive. Any higher order powers will drop out. Okay? So it's coming because dw, that increment behaves like root dt. Okay, and because in the integrand, right, when I do integral w dw, here, you think of this dw as root dt, not like dt, right? So in the normal integral, this is actually dt. So therefore, this higher order stuff, it falls off. But when this is root dt, you have to take some higher order stuff. That higher order stuff is what gives you the correction in E2. Okay. In fact, that's what we've been doing. If you look at the calculations, all the corrections are coming because we can't stop the leading order. You have to go to the next order because this is behaving like root dt. It's giving you more contributions. If this behaved like dt, immediately I would have dropped all of this, right? This will go immediately. It will not become dt. It's a square, quadratic term. But here it's not actually quadratic because underlying the Wiener process is time. And in terms of time, this is not quadratic. It's linear. Okay, that's how this dw squares and all ultimately give you this. Yes?
Can you explain again, like why, if Ito and Stratonovich integrals are both describing stochastic processes, why are we not getting the t term in that? Like, because the normal integral that you were talking about is called deterministic things. So how is that correctly capturing the stochastic?
Correct. Okay, so the question is about basically why Ito and Stratonovich have different answers for the same, nominally same integral. So I'll come back to that in a second. Maybe what I'm going to say will help. So before answering that, what I was trying to motivate is the fact that in Ito, this extra stuff is coming because dw behaves like root dt. Okay, so the normal Riemann procedure is not enough. You need to go to the higher order in terms of dw because dw square also contributes. So now I wanted to think of when you do numerical methods, right? And you try to discretize, you use Taylor series, right? If you have something like dt, you stop at first order. What we are effectively doing now is going to the second order, because you need dw square terms also. They will contribute ultimately in the integral. Now, if you remember your numerical methods course, right, when you do Euler integration of ODEs, right, that's a first order method. It's accurate to dt. What do you do when you want to be accurate to dt square without having to actually take more steps? Remember some modified version of Euler? So there are higher order methods, right, like Range-Kutta, those take many steps. But you remember there is some slight modification of Euler which numerically does not seem much harder to do, but which gives you delta t square accuracy. What is it called? It's called modified Euler or Euler's midpoint rule. Remember, so when you do explicit Euler, you have, let's say, dx dt equal to some function of x, right? What you will do is you will update dx by evaluating the function at the ti minus 1. Right? That's actually what Ito is doing. It's like explicit Euler. Right? So if I have right, my update rule will be xi plus 1 is equal to, say, xi is equal to xi minus 1 plus f at xi minus 1. This is explicit Euler into delta t. That's exactly the equivalent what we're doing in Ito. But Ito cannot stop at delta t. Again, I'm going up and down, okay, but just try to keep track that in the Ito world, I cannot stop at first order. I have to go to second order. And as that's going to second order, that's bringing in funny corrections. But I'm saying, is there a way to directly jump to second order within this same formulation? It's yes, right? You don't evaluate it here. You evaluate it at the midpoint. That becomes Euler's midpoint rule. And that gives you already second order accuracy. And why? You can prove it by doing Taylor series. If you remember, you do Taylor series about the midpoint, right, plus half delta x minus half delta x, and you add them, and you will get miraculously cancellation of second order terms. Directly the errors will become third and fourth order, higher order. Right? And then you can say I'm second order accurate, if you remember that numerical methods derivation. So by evaluating at the midpoint, you miraculously get second order accuracy in this numerical integration schemes. Something very similar is going on in Stratonovich. When you evaluate that thing at the midpoint, it already brings in corrections at the second order. And of course, there will be even higher order corrections, but those will vanish and end going to infinity. Okay, so it's like saying, look, when I'm defining the integral, so now I'll come to the question, right? When I define a stochastic integral, because this dw increments are uncorrelated at each increment. This is what's doing weird things. A normal integral doesn't have that behavior. Right? It's because each increment, this number I'm multiplying and summing, it's completely uncorrelated at each time. That's why funny stuff is happening depending on where I evaluate the g. This is what we just saw previously. The mean value will change. That is inescapable. This is coming because of this extreme stochasticity, if you like. It is completely uncorrelated. Okay? So I have to make a choice, and the choice will affect the answer. I cannot escape this. So in that sense, there is no correct answer. It depends on how I define. Okay? I can get a correct answer for my definition, that's all. And that's very weird. This one, you have to push yourself a little bit. If you just sit and listen to what I'm saying, it's not so exciting, right? But if you really think about it, you have a situation now which is completely unprecedented in any of the math you have done, right? In all the math you have done, there is some axiom, then there is some definition, and there's a definite answer which you can prove. Here it is not like that, right? The situation really is that you have to decide what to define the integral as, and only then you will get correct answers. Okay, but there is no such thing as one answer regardless of where I choose to evaluate. That happens because of this delta correlation of the Wiener process, as we have seen in a very simple way by doing the Taylor series and looking at the mean of the partial sum. So I have to choose where. Now, when I choose the Ito procedure, right, what happens is, by definition, the means are zero. That is the nice thing for mathematical proof and so on. Okay, but when I try to get answers to the integrals, because of this need to go to delta w squared, I get extra terms than the Riemann process. Because if I blindly treat this as a Riemann integral and do the usual manipulation, I will stop at delta w. Because delta w square would normally behave like delta t by n square, and it would drop out. But here delta W square doesn't do that. It behaves like delta, it behaves like 1 over n. Okay, that's why it gives you corrections. But now when you do the Stratonovich, by evaluating the midpoint, something very similar happens to the Euler midpoint rule. You already get the delta W square correction just by evaluating at the midpoint. There will still be higher order corrections because this G is correlated to this. But those will be like delta W 3, 4, and when I sum up, it will be like T minus T naught by n cube, by n square, by n cube, and so on. They can be neglected in the limit of n going to infinity. Right? So by doing midpoint rule, I have somehow absorbed the higher order stuff. Okay, and therefore I get the same answer. What that means is it doesn't mean that my answer is more correct than Ito. That is not what I'm saying. Right? I'm saying that if you view this answer relative to the Riemann, the difference that comes with Ito is because of the dW square. That difference does not come with Stratonovich because it gets absorbed when you evaluate at the midpoint. Okay, but it doesn't mean that the Stratonovich is more correct than Ito. This has no meaning. Both are valid definitions of the integral in the mathematical sense. The question now is, in a physical problem, what definition should I use? So that's what we will come to in subsequent classes.
So Ito has correction up to delta W and Stratonovich up to delta W square. Is that so?
So that's what I'm saying. That language is not correct, right? There's no such thing that Ito is not wrong. Ito is correct, Stratonovich is correct. Relative to the Riemann integral, there are differences, right? Those differences are because of dW square terms in the case of the Ito definition. In Stratonovich, the differences don't arise because the dW square terms kind of get absorbed when I evaluate at the midpoint. Okay, but all of this is very hand-wavy and heuristic. It's just to give you some initial idea. So some motivation for this half. Right? So the half is coming for the same reason that we use Euler midpoint rule. Okay, so Stratonovich realized that if I take the midpoint, I will not get any corrections to the Riemann integral because those dW square type terms will vanish, just like dt square terms vanish in the Euler midpoint rule when you do the Taylor series argument to derive the numerical method. Right? Those second order corrections, because you go forward by a half step backward, when you sum them, those second order corrections vanish. Here also, because I evaluate at this midpoint, right, the dW square terms that come to correct this and so on will somehow cancel out. Here we have not seen it because here I directly use the definition in a nice trick and it gave me the answer. Okay, but that is the underlying thing, and we will see this later on in the course. Okay, there will be many instances where we will have more intuition into why Stratonovich gives you the same answers. But yeah, so I think we'll stop here. Okay, we've already got some initial flavor, at least as standalone integrals. What we will now do in subsequent lectures is try to look at some rules of thumb which we can use to work efficiently with this stochastic calculus, okay, and apply them to STEs. Okay, thank you.